which is sounding very promising. And there's another very useful feature about this test. The probability to get a plus at the ith level is always no smaller than a half. We need this lower bound. Also, it becomes very close to 1 quickly as delta drops to be low enough. So the probability to pass is actually very high after a while, if the error is small. So now I can show you the actual convergence by just visualizing it with some plots for some representative values of the dimension. I'm plotting very high noise here, 99% noise, 1% signal. I intentionally pick a high noise because if you want low noise, you can start, say, if you want 80% noise for d equals to 20, then you can start to look at the curve starting from here, and you should just look at the right half of the curve. So I mean, as well plot more, so that everything is on the plot. So I have I just picked some dimensions that I think may be interesting. And then there is this limit of d equals to infinity that I can also analyze. So this curve shows that yes, the noise will go down. It will go down eventually, no matter how high it is for a start. And this curve has 3 regions, roughly speaking. The protocol just keep recursing, but then the analysis of these curves should be divided into 3 segments. I'll quickly, how much time do I still have? How much time do I still have?
About 20.
Okay, that's good. So then, in this case, I will give the highlights of these curves, and then I will go into more detail about the mathematics afterwards. So the first segment you should notice is this rather strict segment in the middle. I can tell you that if you want to push the noise from 2/3 to 1/3, it takes you no more than 5 iterations. Because the worst case is the d goes to infinity case. I didn't have time to show it, but it turns out that you can prove that the noise reduction is slower when d is larger. So there is a monotonicity relation that we can use. And since we also analyze the case for d equals to infinity, it gives us all the worst case bounds. 5 iterations, worst case. So you can deduce, no matter what the dimension is, no more than 5 iterations in the middle. If it is below half, the noise is below half, it's exponentially decreasing with the number of iterations. Furthermore, there is little sensitivity to d, so these curves are just translate roughly with one another. It's kind of funny. The hard part is the very high noise regime. You can tell for small dimension, then it curves down faster. When the dimension is large, then it kind of resists being reduced. It stays very flat until roughly 1/1 minus delta iterations. Here, the delta 1 minus delta is 1%, and this is roughly 100 here. With a little extra that we'll see what it is. And so let's see this in some detail. The complexity, the sample complexity. Say if I want to push the error from 90% to 20%, then I have to analyze the first segment, the second segment, and the last segment. I have to multiply all this complexity together. The good results first. If the noise is low enough upfront, is no more than a half, then for all d, for all I, the noise parameter delta I with the dimension d is no more than this expression. This expression is, roughly speaking, exponentially decreasing with I. If you want a pretty expression, choose delta smaller than 1/3. Then delta I is no more than 2 to the minus I. So you need log 1/epsilon iterations to get rho epsilon. I'm just upper bounding this with epsilon here and then get the number of iterations. Then we want to know the sample complexity. So at the ith level, I need 2 copies of rho delta I per swap test, and the test passed with probability pi. So I need to repeat roughly 1/pi number of times. So this is how many sample I need for the ith level. And then the whole sample complexity is the product of all the iterations together. So this is the is the actual expression for the expected sample complexity. Then we raise 2 to the power log 1 over epsilon, and we get 1 over epsilon. We multiply all the 1 over pi together. Now the pi is no smaller than 1/2, but it approaches 1 quickly when delta I is small. So when you do the math carefully, you can upper bound it by 1 over 1 minus 2 delta. So in comparison with the optimal qubit result, they are very similar as long as delta is not close to 1/2. These 2 expressions for most purposes is off by a factor of like maybe 3, 5, something like that, maybe 8. While the early protocol only worked for qubit and has more complex circuit implementation. So this is one take-home message, that the recursive sort test is actually competitive, and it is a lot simpler to implement if you have low enough noise, which is hard. Then, one more thing about the circuit complexity itself. How many gates do I need? I need to multiply the log D, order log D, with the number of tests. The number of tests, the tests are actually represented by these non-leaf vertices. Now, if you look at these binary trees, the non-leaf vertices are never bigger than the number of leaf nodes. The leaf vertices are more than the non-leaf vertices. And when I have a union of trees, that inequality still holds. So it turns out that the sample complexity is also an upper bound on the number of tests. So the circuit complexity is the sample complexity multiplied with just log D, and I have the big O up there. So this is my circuit complexity itself. It's pretty small. If delta is not so close to 1/2. And finally, this is the prominent quantum memory if you use the stack implementation, log 1 over epsilon qubit plus 1 qubit for the low noise situation. I already did a summary, so maybe I should move on to the medium noise. Then remember, 5 iterations will get you from 2/3 to 1/3 of the noise. Worst case scenario, 2 copies per iteration, probability to pass at least 1/2. You get a multiplicative factor of 2 to the 10. Then you get row 2/3 down to row 1/3. Worst case scenario, minus analysis. It is a large constant. If you don't like 2 to the 10, I understand, but it is a constant. Computer scientist here. If you want to push from row delta down to row epsilon, for delta being about 2/3, then you multiply the 2 to the 10 to the earlier complexity. And this is the answer. Also, delta is around 2/3, so we can replace the last expression. We get 2 to the 10 3 over epsilon. Now, if you are more careful, you want to talk to the experimentalist, or at least you want to look more respectable in terms of your constant, then you can run the numerics a little more carefully. The constant is 21 for qudits, 121 for 1,000 dimensions. So the 2 to the 10 is a little pessimistic, but it's because of the lazy analysis. And finally, what about the really noisy regime? Since I promised this in the title of the talk, let's call this point when it finally bent down to something like a 2/3, 3/4. It doesn't matter. The difference is a small constant. When would my curve bend down and hit a reasonable noise rate from something close to 1? If D is close to infinity, it's 1 over 1 minus delta. And the finite dimension case is better by quite a bit. I may have time to say a little bit about how we actually prove it. It's quite cute too. We want to upper bound this curve, the delta I as a function of I, and find out where I delta is, I star is, when we reach 2/3. It's not at all easy to analyze. Then we look at 1 minus delta I. So is this thing that is close to 0, and then is the fraction of signal that you have, and it goes up, and then you want to see when it arrives to about 1/3. Again, it is not so easy to analyze. What happened to be easy to analyze is to start from this point, call it 1/3, and then reverse the recurrence. So there is a recurrence that is defined going this direction, and you reverse the recurrence this other direction, and this recurrence can be analyzed. So you start with 1/3 and try to suppress it after I star number of times so that it is smaller than 1 minus delta. Then you know that this is the correct I star, and this is how we find it. Detail is in the paper, but an improved analysis will be included in the revision. And so this is the expression for I star infinity. It is 1/1 minus delta plus a correction term, which is log, the first term, multiplied to 2 plus any positive constant C. 1% is good, 1 in a million is good. If you have finite D, this is a slightly better bound. And when you take D goes to infinity, it actually approaches the top expression. I use double quote here because I removed a few isors for the slide. The actual expression is slightly more complex, but roughly speaking, it behaves like that. This, unfortunately, is just a number of iterations. The sample complexity itself takes a little bit more work to put together, and it turns out to have very sensitive dependence on the parameter regime, which has D and delta in it. So there are 3 regimes I will cover. If D times 1 minus delta is very large, and remember that we want delta to be very close to 1, it means that D is super, super large, then you essentially get back to the first expression here. The 4 comes roughly from the fact that 2 copies per iteration, and at least half probability to pass. Then it's 4 to the power 1/1 minus delta times all the things that we talked about before for the medium noise. This is a very severe expression because the 1/1 minus delta is now in the exponent. For the qubit and Q-tree case, it's actually a polynomial in 1/1 minus delta. Yeah, and we have no comparison. It turns out that we have no comparison because we do not know the optimal sample complexity for large dimension. Then in the other regime, when D times 1 minus delta is much smaller than 1, but D is still very large, it means that the signal is substantially smaller than 1/D. Then we have the sample complexity upper bound as this very small number, 1/D times 1 minus delta, raised to a power which is the dimension D itself. This is pretty bad. If you do state tomography, you do very good state tomography, you do better than this. I'll explain in the next slide. And finally, if D times 1 minus delta is smaller than 1, much smaller than 1, but D is very moderate, then you have a polynomial dependence of 1/D times 1 minus delta. This exponent here is computed like this, so it rapidly increases with D. But for very small D, it's not so bad. So the first and the last item, it is reasonable in comparison with other known methods. There is no known method for the first approach, because if the dimension cannot be bounded, you cannot bound the complexity for state tomography. So there is no other approach we are aware of for the first regime. The second regime, tomography, is better. The last regime, it may be competitive between the tomography method and the recursive sort test, to the best of our knowledge. So how do we do tomography and perform state purification? Remember that you're given many copies of this state. You can ask for as many copies as you want. So if you want to learn psi, you need to amplify all the signal by at least 1 over 1 minus delta. Luckily, this part I over D does not cause you a lot of problem if you measure, say, the Pauli's. Then you want to find a description, psi prime, so that the trace distance between psi and psi prime is no more than epsilon. Then you just output psi. You don't output the state which looks like a row epsilon, but it is close enough, so that looks like a reasonable way to purify the state. If you want it to be streaming, you want to measure copy by copy, D will be raised to the power 2, not 1. But otherwise, the exponent for all these parameters is either 1 or 2. It is quite gentle for state tomography. I already said this. This is equally streaming. So state tomography is looking very competitive against the recursive sort test. I do not know what happened if we can compare it with the Sher sampling. We do not know whether this is optimal or not. So this is a big open problem. I should wrap up. Let me tell you why we studied this problem. It is about query complexity with 40 oracles. I don't want to define these things, but you probably have heard of Simon's algorithm. That's the algorithm before Shor's algorithm. And the first algorithm, which gives you an exponential speed up without a promise in the input. Suppose the input size is D, which is 2 to the n. Then suppose it actually involves preparing these pure states, and then you try to learn the parameter S from these states. It's a vector S that you want to learn from these states. But suppose this state is actually noisy in the form that we discussed. You don't know what this is. You prepare from the quantum algorithm. Odette Regev actually found out in 2010 that the best quantum algorithm that he considered seemed to require exponential in n number of queries. And we seem to be losing the advantage over the classical algorithm. But if you use the recursive sort test for the delta lower than a half, you only need 3 over epsilon copies to get 1 copy of row epsilon. And then you want to set epsilon to be 1 over m. If you do that, your algorithm will basically work okay. And you need to repeat, you need this number of copies for 1 round of the algorithm, and you need to do it m times because S is an empty string. So you need all the m squared queries. Worse than before, but it is still polynomial compared to exponential. So we restore the speed up, the quantum classical separation for Simon's algorithm using the method that we showed. As a second example of connection to algorithm, the quantum majority algorithm is very recently proposed by Berman, Linden, Manchinska, Montanaro, and Ozols. It says that if you have n bits, A1 through AN, and they're given to you as quantum state in a shared but unknown, in a common but unknown basis, and you have to output the majority A in the same unknown basis, then they call it the quantum majority problem. And they propose and find an algorithm to perform this. It turns out to have a very similar complexity as purification, and in fact, if you know how to perform the quantum majority, you can perform purification and vice versa for the qubit case. So we hope that our result provide a generalization of quantum majority algorithm for larger dimensions. And finally, we hope that there is some connection to cloning. And let me just wrap up with one mention of an extension. I'll skip item 1. As long as you have a mixed state with a non-degenerate maximum eigenvalue, the analysis that you saw today can be extended to that scenario with some work. And this hopefully will have some interesting applications, including learning of states and so on. So I'll stop here. Thank you very much for your attention.
Right, thanks very much for the perfect timing. Any questions from the audience? Okay, maybe I'll just ask one quick question. So I noticed that in many of your expressions, for the complexity or maybe the expected number of copies is the scaling in epsilon is 1 over epsilon. Is this actually known to be optimal? Could it be improved?
The short answer is that I do not know.
Okay.
They do look like they always appear to be 1 over epsilon.
Okay. And maybe a second question would be, how hopeful is it that we can generalize these results to, let's say, beyond white noise?
You mean the noise being I over D?
So the error model that you consider is mixing with the maximally mixed states, which is maybe not always the case in realistic experimental situations.
Right. As long as I'm mixing, as long as after the mixing, the signal state that I want remains the principal eigenvalue.